Det ligger i clarifications. Ja. Vet du vart HDMI ligger?
HDMI-kabeln ska vara...
Vadå? I clarification svar på en fråga eller?
Ja. Projektorn, hur startar man den?
Ja. Här.
Och ljud och allt. Ljud och allt funkar också. Nej.
Ja.
Perfekt.
Jag vet inte varför utbildningen bara är så dålig.
Hur gick det? Sådär. Läste du det?
Nej, jag läste aldrig det. Jag skrev typ olika lösningar på det. Men,
Alltså det är ju bara att göra en kurs. När det egentligen typ du har en DP med diktmask, så är det diktmask och sen vilka möjliga slag finns det, så kan du kombinera dem. Ta två disjoner. Ja, så borde det gå. Det var inte dumma lösningen. Alltså,
och luta
Python-lösningen. Det var så 5 på morgonen. Python-lösningen för runtime. Och då var vi tar bara och flyttar ut den. Och så ser vi att det ska jättesnabbt. Och så blir det en second time. Egentligen vill
jag gjorde en lösning på Python.
Det var också kul. På typ andra eller första uppgiften stod det 1 mindre lika med typ 1000.
Eller nej?
Vet du vad? Jag kan bevisa att det är sant.
Det är ju inte fel. Det var inte särskilt hjälpsamt. Också, alltså, hissarna. Det var jättetydligt för vad man skulle göra på hissarna. Eller hur hissar fungerar.
Kollar på Gymnastik eller Average Spanning Tree. Det var mina problem. Average Spanning Tree är pretty cool. Det är ta alla Spanning Trees i en viktargraf och så beräkna averagen av vikten av dem. Och det är lösbart.
Och Spanning Tree bryr sig inte om vikterna när det gäller alla Spanning Trees.
Stay tuned till läsningsgenomgången. Men behöver vi något mer innan vi kan köra igång? Ja, Loka här. Är det bara vi som kan presentera lösningar?
Victor ville väl presentera ettan eller något.
Victor! Men skärpning för honom, för vi ska ju se börja nu.
Han måste ta bara Luka.
Ja.
Okej, har vi ljudet på?
Ja, det ska vi ha. Victor sa att det funkade.
Vänta, kan de höra oss nu?
Jag tror det. Men Victor! Du ska presentera eller vill du presentera decimal deletion? Vill du presentera decimal deletion? Ja. Okej. Solution presentation time. Please sit down or something. Just get ready for it. Okay. So I hope you had fun. The competition was a bit harder this time than last year, but I hope that you still had fun solving the problems. So now we're going to go through the solutions, and then after that, then we're going to reveal the scoreboard at the end. So first off, the first problem, decimal deletion by Luke Gustafsson and Victor Saul.
Yes.
Wait, do I have to stand like here?
Do whatever you want.
Yes, I am a ghost that no one can see other than the people in this game. Anyway, so basically, this is the first problem in the competition. Pretty simple. You just read the input, round it, and print. And then I think one problem we had when we were developing the problem was that Python rounds towards even numbers instead of just away from 0. So that's why instead of always rounding up, we just have it so that like if the number ends in 0.5 or something, you can round it in either direction and it'll both be accepted. So yeah.
Yeah, so point being, floats are actually scary.
Yes. Joshua was correct.
Okay, next problem. Elevating the prank by Julia.
Yes, awesome. So in this problem, Luke travels from floor A to floor B. He is already in the elevator when the problem starts, and you in the problem have clicked on n different floor levels, and you want to find out how long Luke has to suffer inside the elevator, and rightfully so, because he actually did beat you in last week's programming competition. So kind of a bad move. So the problem or the solution basically is that you calculate the number of levels Luke is traveling from. So he is starting in the elevator, and then you just take that number of floor levels, and you take it times 4, and then you also want to see how many levels that you have clicked on are actually between A and B, and it's not inclusive. So if you click on the level that Luke is starting on, then that really, or that he's getting the destination, that won't really make a difference, because because
the elevator is already
already there. So it was some edge cases, but all in all, just making some arithmetic. And here we have a solution by Rebecca. Basically just read input, and then here you see if it will stop, and so on, and then you just calculate it in the end. All right. Yes, and then we had some comments on that, instant opening and closing is not how elevators work, and I don't know what you mean, because that's how the elevators work in Emilsborg at least. So, yeah. Anyways, the next problem is porridge boxes. So in this problem, we have someone called Julia who really, really loves porridge, and she can make porridge a given number of days due to a busy schedule. And in order to be happy, she needs to eat porridge at least A out of B days. A possible solution here is to investigate for, okay, if we have a given, let's say we do have a given refrigerator size, how many days will Julia be happy if the refrigerator is this big? And then there were some subtasks. So you could find an optimal refrigerator size given small input if you just brute forced. But for full score, you needed to do binary search to find the optimal optimal refrigerator size. And a key insight here is that once you have a given refrigerator size, then you can just make porridge greedily. You can just make porridge the days when you have enough refrigerator room for the leftover refrigerator or the leftover porridge to be stored there. So we have an example solution here by Joel. So here first we have the happy days where we just have a function where we calculate given a specific size of the refrigerator. You just calculated, okay, how many days will Julia be happy? and then here we do a binary search, to see if what the optimal or the minimum size of the refrigerator that is still enough big enough for Julia to be happy a given number of days. Yes.
So the next one is 24 game made by Luke Gustafsson and Victor Son. So this problem is like you can't really do anything too fancy with it. It's just you brute force all possible solutions in, like, you need to be a little clever for it not to be too slow. So subtask 1 and 2 is basically just you do brute force, but it's too slow. So the full solution can look something like this, where we can do like a BFS, where we have like the state is, okay, we have all of these numbers, and then we can change our current state by, we take two of the numbers, combine them by maybe doing plus of them or something, and then adding them back into the set. So we repeatedly just try all ways of combining different numbers into new ones, and then along the way we maybe store the way we got here, or we could reconstruct it at the end. So there are some caveats that you need to make sure that you don't accidentally divide by 0, because that could make things weird. And you could also have some floating point positions because of division. So I think some people manage to get solutions using little floats, but if you want to be really sure, you can do rational arithmetic, which will be fast enough. So unfortunately, due to some technical errors, the time limit was quite tight. We had hoped for it to be higher, but I think that there are solutions that are quick enough. It might, even Ulla managed to get one in Python, so it is solvable. Yep. Next one is Sneaky Mastermind by Luke and Julia.
Yes. All right. So in this problem, we have Hugo and Rebecca, and they're playing Mastermind. So this is a game. You can see the picture here, given a code, you are tasked, or Rebecca is tasked, to find the solution or the code, and Hugo will give her two integers. One integer is so this many pegs were in the correct position and have the correct color, so are completely correct. And then we have the second integer is this many pegs had the correct color, but are in the wrong position. The sneaky thing here is that Hugo actually at most one time per game will give the wrong answer. So your task is to still find the correct code, but knowing that he could cheat once per game. And it's also an interactive problem. So given the number of guesses, then you will get different points.
And this problem is also like it happened in real life. That's why it's a problem. Just a fun fact. So, like, example of how this game works, the judge tells the program like how many pegs we have and how many different colors we can choose from. Program guesses. Maybe the program returns whatever. Maybe it's lying. For example, here we guess 4 A's and then guess 4 A's again, getting different answers. I guess technically we don't know which one of those are lying, but we know that one of those are lying. And then we guess again, and we are really lucky, so we guess A, B, C, A, which is the right answer. And we get, we have 4 pegs in the correct position and 0 correct color pegs in the wrong position. And that's guaranteed correct since the lie has already been used. And so we can guess A, B, C, A. And the number of queries that are counted by 4 is guesses. Okay, so N goes up to 10 and C goes up to 15. It's like heuristic scoring. We have many test cases. You get the average, of your like test case scores as your total score, and the score works in such a way that on a test case, if you're like sufficiently good, you get 100 points. Otherwise, you just get very few points. And the hope was that it should be. So we hoped for people to get maybe like 15, 10, 20 points, or like very few points. But then like among people getting more than 50 points, people would get 100 points. That maybe didn't quite happen in reality, but it's like very possible to get 100 points. So it's like heuristic, but it's not like there are very diminishing. There aren't diminishing returns, but rather you can just finish the problem by having something that's good enough. So returning to the bounds, how many ways can you? So for each of the n slots, you select the color. That's 15 to the power 10 possibilities. That's a lot. But for some test cases, n and c are smaller. And let's first think about those test cases. And if that number is like small, maybe 100,000, maybe a million, maybe 10,000 only. For example, in real life, n is 4 and c is 6, and then it's like a few thousand. Then we can have then we can make a list of all the possible games and like play and figure out which ones we can exclude because it's not possible to be in that possible game. Also, if we don't care about efficiency, we can guess twice, and then if those don't match, we guess again, in order to like in just a bounded number, like in 2n plus 1 queries, make n real queries without having to care about lying being possible. We can, for example, then if we have this set of possible like remaining possibilities, we can pick any from them randomly, and that kind of works. So if you do this, you get some points. And now we want to improve this. So regarding the lying, it's kind of inefficient. For example, in the case that Hugo doesn't lie, to like always guess things twice to make sure they agree. But it's also kind of unnecessary. So we can guess some things, and then so the problem is that if we guess something that could be correct, it could be a lie. So we cannot exclude possibilities rejected by that guess directly. But we can mark those possibilities as once rejected. And then if we do another guess later and that rejects the same possibility, then we can reject that possibility. And that means that in practice, instead of doing like 2n plus 1 moves, you get like n plus 1 moves for n real effective queries. So that's a way to deal with cheating. Right, and if we have this, we're still then we play fairly well on small games. But if c to the power n is huge, we can't use this because we can't enumerate all the possibilities. So let's care about that next. So there might be multiple ways of doing this, but one idea that we used for the judge solution is to first figure out what colors, like you could figure out what set of colors, but here we figure out what set of colors, and for every colors, basically we figure out for every color how many of that colors are in the answer. And that's obviously fewer than c to the power n. How many are there? Well, if we have, like this is a standard problem of if you have c minus 1 plus n items, and we have like c minus 1 of them being walls and n of them being items, then and also we don't care about like the internal order of walls and things. We get that the number of multisets are n minus 1 plus n choose c minus 1 plus n choose c minus 1, and that's small, or like reasonably small, so we can play the game in the same way. So let's have an algorithm like this. We create candidate multisets, and we play randomly by like picking a multiset and then like taking the colors in that multiset in some arbitrary permutation, playing that, and then when we get the reply back, we can filter multisets. And due to the lying, we still need to use the 2 strikes and out approach. And then once we have just a single multiset left, then then how many possibilities do we have left? Well, in the worst case, we have 10 factorial, since if all the colors are different, we can like permute them in any way and they look different. So we might have also a few million possibilities left, but that's fine. We can construct those and we can play like before. And this is the general approach to play well. There are a few tricks you need to use in order to not like play badly in some cases. For example, if we have used a bunch of queries for the multiset filtering, then we have received information on correct positions from those queries, but we haven't used that, since when we filter multisets, we don't care about place, like the actual position of the place. But we still have those queries, and we can use that information once we have constructed the 10 factorial permutations to filter. And then finally, I'm not sure if this is super important, but you can also, if the multiset filtering like leaves you with no, so if the one multiset that's left after the multiset filtering has been rejected by one query, that one query must have been a lie. So we know that lying has already occurred, and we can do one strike and out for the rest of the queries. And that works, and that gives 100 points. Or rather, it gives like 95 points to 100 points, depending on your seed, but like submit 2 times, 3 times, and you get 100. And basically, we made our scoring so that that strategy would work. That so we didn't want a situation where people tiebreaked on having 95 versus 96 points. So if you get like 90 points, you can probably get 100 points fairly easily. Plus there is some noise. Technically, you can play better than this because we picked random moves from a set, and who knows if that's the best. We can play better by like evaluating, if we play this move, what are the possible game states after, what are the probabilities, and how difficult are those to solve, and so on. And like probably people have seen a 3-Blue-1 Brown video talking about Wordle and information, and that's basically this. But it turns out that for this problem, we already get so much information. Like the search space is already shrunk so much for each query that picking better moves doesn't really matter. It like maybe decreases your decreases expected value of moves by like point something. But you have massive slack space, so you don't need to do that. So you can ignore this. And no one got 100 points before the freeze. Maybe 50 points before the freeze or something. Yeah, this is empty.
So now we're going to talk about Hume aesthetics. So the problem, you actually need to read it very carefully. Because it might seem like, oh, these numbers are huge. How are we ever going to do anything with it? But what we can realize is that, okay, first off, we can actually rescale our input.
Should we recap the problem statement?
Probably, yeah. Whiteboard pen, maybe. So the problem is basically that yeah, it's too bad if you're watching from home. You can try to watch. So we basically have we have a barbell that at the start weighs 20 kilograms, and then we have a lot of weight plates. So maybe these ones weigh 20 kilograms each, and so we get like a bunch of weight plates that always come in pairs of 2.
And they have different weights, like some weigh 20, some weigh 100.
Exactly, and it can be multiple of each weight. And then we want to, this is like a competition, and first we want to lift a barbell weighing like 100 kilograms, then 200, and then maybe 50 or something. So these are quite arbitrary what we're gonna lift. So now we're going.
50 is impossible. It's a multiple.
Yeah. Now the way that we can use get different weights is actually quite realistic. So we can take like one of the plates and add it to both of the sides of it, and then that increases the weight. And then we can take the outermost of it and remove it. And one crucial part is that when we place weights on it, they must always be in decreasing order. So if I have like 20 here, the next one must be 20 or smaller. And now we want to find like what is the least number of moves needed to lift all of these in order.
And moves are removing the 2 plates or adding plates.
Exactly. And it's also guaranteed that there is always a solution, but that isn't too important to the actual solution. So the first thing that we have to notice is that the input is actually like inflated. So first off, we can remove 20 from all the target weights because the bar weighs 20 kilograms. And then we might as well divide all target weights by 2 because the bar is symmetric. So now we only need to take care of one side of the bar. So it basically becomes like we have a single stack now. Then it's also, this is very important, that all of the weight plates are divisible by 10. So we can just divide everything by 10 after we have done the minus 20 part. And I didn't want this to be the case originally, but then it ends up being like, oh, Sven can lift 100 kilograms. But I mean, look at the dude. He can lift more than that. So we decided to scale everything up so the problem became more realistic. So now we can move on to solutions. So as we said, we only need to take care of a single stack. So in subtask 1, there are very few weight plates. So we can do a single DP where we have like where we basically keep track of like which weights are on the plate right now. And because there are at most 15 of them, each one can be on there or not. So it's like 2 to the 15 possible ones. And we also keep track of like which weight are we trying to get to now. And if we actually implement this, we might notice that like, okay, this runs forever. And it's because this DP has cycles in it. So we actually need to do Dijkstra. So it turns out to be like a shortest path problem. So that's like in general, if you have a DP problem with cycles, throw Dijkstra on it and it should work. But okay, so this handles like K being 15, but in reality in the problem, K is like 2000 or something. So we need to be a bit smarter. So the key insight is that after we have rescaled everything as according to the first slide, all the target weights are actually like less than or equal to 39. And one can show or just that you've heard it before, like there aren't that many ways to sum to a certain number. So what I mean is like, if we have like, okay, we want to have a stack of weight 5, there aren't like that many order stacks that can actually achieve it. So maybe it's like we have 5, 4 and 1, 3 and 2, 3 and 1 and 1, etc. So this is like the number of these isn't small, but it isn't too large either. I think for 39, it's something like, I don't know, maybe 50,000 or something. And 29 should be even smaller. So these are called partitions. Now we're going to do a DP based on the insight like, okay, we're only going to care about the partitions. So first off, we create actually explicitly all of the partitions. So like for each number, what are these sets that can sum to? So like for 5, we generate all of the sets that have some 5 and are sorted. And then this can be done pretty simply just doing a recursion and not generating anything twice. And this would run in like O of the number of partitions generated, which is fast enough. And then we do a DP on this. So we have like, so our state will be something like, which weight are we trying to get and what is our current stack right now? And then going from one stack to another, we can realize that, okay, the cost is just, so we have like 20 and 10, and then we have like 20 and 5 or something. So in general, what we're going to do is simply like, might as well keep the ones at the bottom that are the same, and then remove all the ones above. So it turns out that the cost of going from one stack to another is the sum of the length of the stacks minus 2 times the longest common prefix. which can just be computed in a for loop, basically. So if we have that pi is the number of partitions of I, then our solution runs in like all of the sum of the partitions of all numbers less than 29. And then when we actually do the DP, we have like, so we have our state is like the target, which is less than n, and then which partition are we on currently. And 29 has the most, so that's the worst case. And then going from one to another, we need to check like for each partition, which partition can we get from. So it will end up in the partition squared, which is fast enough for 29, but not for 39. So we need to optimize this. And as most DP problems, the easiest way to optimize them is probably by speeding up the transitions. So that's what we're gonna do. Because when we look back at the formula, like this, let's see where it is. Yeah, this formula is actually quite simple. So now, like if we are at state A and we want to check like which is the best one to come from, like we already know length of A because we are in the R, and then the only target's variable is basically the longest common prefix. So what we can do with, okay, prefixes, maybe we build a prefix tree or a so-called trie. Unfortunately, I haven't drawn it, but we basically create, like for each number, so maybe this is like, I don't know, first one is 20, and then we have 10, or maybe there's another one with like 20 and 30. So this, no, this is impossible. Let's do 30, 20. So this represents like, okay, we have the stacks, one with weight 30 and one with weight 10. Then another one with like weight 20 and another one with weight 10. So this, so like we know, so we add all of this into the same data structure, and then now we know that like if we traverse this data structure with our current weight, we will be able to know like the longest common prefix, because that's like the node that you're at. So store like for each node, what is the shortest one that achieves this prefix. That was probably a poor explanation, but you'll be able to figure it out probably. So this now, instead of like being the partition squared, it's basically linear, because the all weight stacks will be pretty short. They will be like at most 39, and you only go like 39 deep in the tree. Any questions? Nope. Okay, next one, average spanning tree. So fun fact, this was not my problem idea, it was Gustav Kalander. So he thought like, okay, we have this and we can use like some Markov chain to uniformly sample a random spanning tree. So we can actually like approximate this quantity at least. And maybe that could be a problem, I don't know. But then I realized that no, we can actually solve this exactly with a deterministic solution. So the first subtasks are not at all related to the full solution. So the first one, we just try like for each edge, use it or not, and then check is this a spanning tree, and if it is, add it to the answer, and then like we take the total weight of all spanning trees divided by the number of spanning trees, which would be the average. So quite simple. Next one, it's basically the exact same idea, but it's just that, okay, we only ever need to choose like a subset of the edges which is of size v minus 1, because that's how many edges there are in a spanning tree. So if we implement this a bit carefully using some recursive function that only like generates all of the EQs v minus 1 subsets in that time, then it runs in something like 10 times 10 to the 6. And then this, I actually really like this subtask. So it's so the idea is that we do the exact same as the one before, but whenever we add an edge, so we gradually build up our tree. But if we ever add an edge that creates a cycle, then there's no point continuing on recursing, right? So if we could quickly detect when if a cycle is formed by adding edges, then that would be very nice. So you can think of maybe, oh, union find can do that quickly. But the problem is that union find, usually you can only add edges but never remove them. But in our case, we only like add them and then maybe undo the last one. So the insight is that in union find, each edge addition only changes like a constant number of things, so we can just keep track of like what has changed in it over time. We have like a stack of these changes, and then we can undo the last one. So this will run in something like the number of spanning trees times log of something, but it can be implemented pretty quickly. So in the last subtask, so the idea is basically that we're going to count this in a different way. So the idea is that for each edge, we're going to count how many spanning trees use this edge. And then if we take like for each edge, the weight of it times the number of spanning trees that use it, that in total is going to be the total weight of all spanning trees. So if we could compute that quickly and also compute the number of spanning trees quickly, then the answer would just be like that total divided by the number of spanning trees. But it's not obvious at all that you can actually count the number of spanning trees. But it turns out that there's some weird, you create some weird adjacency matrix, you remove a row and a column, and then you compute the determinant of it, and that turns out to compute the number of spanning trees in cubic time. I have no idea actually why it works, but it does. And then, so this allows us to like count the number of spanning trees in the graph easily, which was like the first part, which is pretty easy. But then we also need to count like how many spanning trees use a single edge. So what we can realize is that we can basically, so we go through for each edge. So say some graph like this maybe. So what we will do is that we will basically contract the edge. So what this means is that we take both of the endpoints of it and merge these into a single node. And this graph will be like, this will have like, the number of spanning trees of this graph is the number of spanning trees of the original one using this edge. The problem is that, as you can see, there can be multiple edges between pairs of nodes, but it turns out that the formula works for it too if you just do it correctly. And this will then, like for each edge, you do v cubed operations, so v cubed times c in total. But it, in practice, it turns out to run like v squared times c, but I don't know if that's provable or not. It's probably because like most of the matrix will be the same, and maybe you can use that. I haven't looked at like the determinant code that I used, but maybe it uses something like that. Unfortunately, Python was too slow, and this is because we didn't use a Python solution. I thought like C++ runs in 0.04, so I thought surely 1 second will be enough, but maybe it's just as slow. I think that it will be fast enough if you don't reallocate the memory, just use a single matrix and fill it in again over and over. But if you just do it naively, I think Nils and Harry, unfortunately, lost 100 points due to Python being slow. So now the last problem. Oh yeah, also a bit of a side note. If originally we wanted to have like bigger graphs where it would be a problem that the floats got exponentially large, but it turns out that we can even compute the quantity for large graphs, where if we look at this expression, we can separate out the terms on the top divided by the denominator, and then we can compute each log of it, and that's nice because the determinant is the product of all eigenvalues. So we never, like all intermediary steps are small, and we work in log space, so we won't have precision issues. But unfortunately, the algorithm is too slow to actually encounter these exponentially large values. So this was not needed at all. We can just do this using doubles and it should be fine. Yep, spaghetti cutting by Luca.
So we had a bunch of problems getting a correct Java solution, and that's why we put it last. And it turns out we had a bunch of people solve it. I think 4 people before the freeze, and all using like something that's different from the Judge solution. But let's not get ahead of ourselves. So the problem is that we have a bowl of spaghetti, and we have strands, integer lengths, and we will perform cuts. And each cut, we basically pick a place to cut uniformly. So a strand that's like twice as long, it has essentially twice as many places where you could cut it. so that strand is more likely to be picked. And then at the end, once we're done, and we like sample uniformly across cut locations, and then at the end we only eat the pasta that's sufficiently short, and we wonder what's the expected edible length of pasta. A thing to note is that A and B are only up to 100, but the problem statement talks about it being B micrometers long. Maybe the pasta should have been millimeters long instead. But that's just the oopsie on our part. So example of how this thing works is that if we have a strand of length 4, so like here's a strand of length 4 for 9 segments of length 1, and we can't cut at the ends, so we can only cut at like places between the strands. So there are B minus 1 possible cutting points. So we have some bounds. Like M can be large, M and A and B can be fairly small, but we have a subtask, and that's a single strand of pasta. So let's first solve that. And this is the judge solution, and I can talk about the solution people actually use later. So let's do a DP that says, given this many cuts and a strand that's this long, what's the answer? And then, of course, the total answer would be for all of the M cuts and the entire B. So if we have capital M, capital B here, we get the answer to our problem. So what's this DP? Well, if we have many cuts, then we're guaranteed that there are no long pieces left afterwards, because like because every time we make a cut, we will like shorten the length of the pieces. So if some inequality holds, then we can eat all of it. Otherwise, was that a question? No, okay. Otherwise, one way to do deeper transitions is to pick a place to cut and then like transition into those states and then multiply by the probability of doing that transition. So if we say cut at some place B, and we designate some number of our remaining cuts to be placed in like the left strand of those two created, then we transition into these states, and the probability of doing that is the probability of picking that M prime B prime, and that would be this. So what are these probabilities? Because like this DP is fine, but we need to get those probabilities. Wait, are we missing a slide? Okay, I appear to have deleted a slide. So since we pick a place to cut uniformly, this probability of getting B prime is like constant, because any location to cut is equally likely. However, given two strands of shorter lengths after a cut, the probability of getting exactly M prime of those cuts into the left strand is not as obvious. Okay, I think maybe I lost two slides. So we can think about this as, do we have a pen? Yes. We can think about this.
Maybe
Having, okay. Yep. We have our strand. So like we had this big strand, which is like a big box of possible cut locations. Then we made a cut. So now we have like two boxes of cut locations, and we want to ask the question of, so we have a box of like size A and a box of size B. Well, no, A and B are already used. Let's not use those. We have a box of size big X and big Y, and we have some number M of cuts, and we say that M prime of those be here, and M minus 1 minus M prime be there. So that we used one cut here, and then we distribute the remaining cuts in some way. Let's call this small x. Let's call this small y. We want to know the probability of putting like x of the cuts in box x and y of the cuts in box y. And that would be this expression. So we want, so like the first cut here can be made in like x different ways, and then x minus 1 different ways, since when we do cuts, the number of possible locations to cut decreases. That's the first time. This is the product of like x times x minus 1 times so on, total of small x times. Same thing for putting the cuts in the other box for this term. And then each of these cuts was from some number of remaining cut locations, and that's x plus y times x plus y minus 1, and so on, for the x plus 1, for the x plus y different cuts. But then we, of course, can, for example, if we order our cuts, we don't have to first cut x and then y, we can do it in different order. So we have like distributing the cut in some orders, and that's the x plus y choose x fit. So this is a quite nice like probability subproblem of distributing cuts to boxes of and we need to compute this. And for this problem, we have like this is just in a single strand. So x and y and x and y, all of those are like less than m and b. So there are 100, we're at 200. We can pre-compute. We can pre-compute factorials and then do prefix sum on the factorials, but using logarithms in order to not have huge factorials, because otherwise we get huge numbers. And that means computing this expression in constant time. But in the transition we had this double sum, so we have like b squared transitions. And our states was also, it was m and b. So I guess technically it's m times b plus this, but in practice it's b squared. So we have b to the power 4, whatever that's called, as the total DP time complexity for a single strand. And this is the judge solution. You can do this quicker. I'll come back to that. But this was the intended for a single strand. So now let's solve this for multiple strands. And from the first problem, we computed a DP. Let's call that DP1 now instead of just DP, which says for some strand size, for some number of cuts, what's the edible amount, expected edible amount. And now we can like insert the total strand length and get something similar for some number of cuts on the original strands. So we can make another DP with states now being how many strands we have in our box and how many cuts we perform in it. And we can like populate the first row of that DP using using the values from the first DP. And then we can make transitions here if we like add multiple strands. So if we have a pile of strands with some number of cuts, we could take those piles and distribute it to two piles of size n1 and n2, and then decide somehow how to place the cuts. That would be this expression and this Pm prime also. And then the question, of course, is what's this Pm prime? That's actually kind of the same as what we just did on the board. But now this x is instead the number of cuts per strand times the number of strands. So this is the number of cut points in a strand group instead of on a single strand piece. And these number of cuts are the same. It's m prime and m minus m prime. And now we still need to compute this factorial expression, but now the numbers x and y, capital X and y, are huge, since we can have many, many strands. So we can instead compute like capital X times capital X minus 1, so on until capital X minus small x, we can just linear loop to compute that. Maybe you could use the gamma function. I'm not, like the logarithm of the gamma function, but I'm not sure about that. So we get like slower transitions, but it all works out in such a way that doing this transition from one group of pasta, like combining two groups of strands in m squared, that's 200 squared. But we only do that logarithm times if we compute this for groups of 1 strand, 2 strand, 4 strands, and so on until like, I don't know, 1,024 strands and so on. And it's basically fast binary exponentiation to compute the final value. And we get some time complexity which is like well aligned with the bounds, like something, some hundreds of millions. Should be fine. But now on to how people actually solved it. People didn't even have powers of 4 terms. They had like things sized in the millions rather than hundreds of millions. And the idea, so while I wrote this slide, I didn't quite understand how this worked, but now I do. So basically, we say that this thing with distributing cuts to boxes doesn't need to, like, so previously we used it if this is a single strand and this is pieces of the strands. And we also used it for like groups of strands, but we can use this directly with like this being a strand. So we can say that x and y, so y might be all the other strands and x might be this strand. So we compute for a single strand what's the expected number, like what's the probability of the number of cuts on a single strand, right? We do that by calling this, I guess, once per n prime. And then for that strand, we know for this many cuts, we can do, I guess, dp1 basically, or something similar, smarter. And then we have for this one specific strand, the expected edible amount, and then linearity of expectation means that we can just multiply this by n directly to get the expected across all strands. We don't have to do the binary combining. And if you do this, like your program runs in a millisecond or something. So here's an example of the code to solve this using the quick method. And it's like very short and simple, although the math is, yeah, it's not the math that I computed when I first solved this. And that's the last slide.
So yeah.
Do we have any questions on any problem?
Or from the chat.
Right.
You can write them in the chat and we'll check.
Nope.
So if that's the case, then we just want to thank you all for participating. And we would like to announce the winners.
Yep.
Should we scroll back to scoreboard?
So there may be a working with Solver. No, this is the wrong one. So let's see. We'll try. Maybe this will work. Let's see. Undefined. Nope. It does not work. Okay, we're simply gonna have to do an ugly solution of simply scrolling up the scoreboard. Let's see. I'm gonna directly disconnect this. De blev spoilade i livestreamen, men synd för dem. Yeah, there we go. So we're gonna do the super advanced technique of simply scrolling up the scoreboard. So we can do the first like top 30 of these quickly. Yep. Kul att se att det här ska vara...
Just continue.
Yeah. So now we're moving into the top 20 of them.
So very well done.
Yep. Strong performance overall. So now we're getting into the top 10. Yeah, I think, yeah, very good job to Olle. He was
our first full solve on the last 4, like
the spaghetti cutting.
Yes.
The spaghetti cutting. It's one of the 4 hardest problems.
Yes. And now number 4 turns out to be Nils Gustafsson. Unfortunately, I think he had a correct solution on every spanning tree, but it was too slow due to being Python.
We apologize, Nils.
Yes. And the next one is David Wern. I think he's the best
also
one.
Happens to be the best on site. So
Yeah.
congratulations.
And now number 2, who could it be? Morten Wiman. Very strong performance, solved everything except for Sneak Mastermind. And big surprise, the winner of Chalmers 2024 is Simon Lindholm. He was very close to solving everything, but he didn't quite manage to get 100 on Sneak Mastermind.
So I looked at the submission from Mastermind. It gets CUD on like some test case. I'm fairly sure that if Simon just samples a bit fewer or like breaks the loop if you're close to the time limit, and plays moves slightly quicker, then he'll get 100 points.
Yep. So that was that. No, it was not actually everything. So this was it for the scoreboard.
But we'll end the stream here, I think. So goodbye to everyone who's been following online, and I hope to see you next year.
Yeah. So the rest is for on-site only. So maybe you should come to on-site. Okay.